Welcome back, everyone. So as you probably know, because of the Landing Kids audience today, that there's a quiz. Again, the quiz will be the last 30 minutes of the lecture period. So if it gets to be really close to 3:50 and I'm not stopping, please remind me to hand out the quizzes. And as a reminder, you will not get a computer, calculator, or phone to use on those, but one side of one sheet of paper. So if you haven't made a kind of a cheat sheet yet, you can start doing it now.
I hope this is not tough, but when I was making my cheat sheet, I noticed in my notes that the turnout plotting requires n independent random variables. Do they have to be from an identical distribution?
They don't.
They don't.
Yeah, they don't. Yeah. So usually when you apply it, they are, but in some cases they aren't, and it still works. They just need to be independent, and they need to have this upper and lower bound up. Yeah.
Is that just because the analysis we do is on X bar random variable, which I guess kind of takes care of the margin that might occur when you don't IID random variable?
Yeah, so I think the proof, I think it's just the proof only uses the independence of it. So I don't have a great, well, without reconstructing the proof, I don't have a good reason of why. It's if you're thinking of it as a generalization of like the central limit theorem, then the central limit theorem is assuming stuff is IID, so they're all from the same distribution. So as a generalization of the central limit theorem, then you would think of it as IID, but the proof doesn't require it. It doesn't even require that they have the same bounded range for all variables, as long as the difference between the bounds, you take the sum of that difference squared, and there's a general form that doesn't need any of that. The form I gave you just needs independence. So for this class, that's the only thing we'll use. Yeah. But yeah, it's an interesting kind of nuanced question that for the purposes of this class, you probably don't need to know the answer to. But in general, there are much wilder forms of these that try and relax all these sorts of assumptions. Okay, so homework 2 was due Wednesday, and then homework 3 we'll have out by the end of break. So over fall break, you won't have any homework out. Hopefully this is a good strategy. And then quiz 3 won't be until I have on, so it won't be until November 11th, right? So it's going to be a more than a month until the next quiz. We'll go over cross-validation after break, and then we'll start on gradient descent and dimensionality reduction and stuff. The plan for the lecture today is there's a couple of things with polynomial regression I wanted to kind of just go over briefly, and then after that, either I can go through the proof of why that expression gives you a closed form, or you can ask me questions about kind of the material that will be on the quiz soon. All these options are fine. Or I can just go through examples of things. This is kind of a slack class. There's one small example I plan to go through first, but then we can open up a short question now.
Yeah, we were actually looking at a homework assignment on the ones that just got graded, so maybe that's something possibly go over. The homework that was just turned in.
Oh yeah. So homework 2 just came back. Yeah. Oh yeah. There was one. The first question, 1A, was a little bit tricky. I think I heard no one got full credit, but there are a bunch of people only lost 2 points. So I can go through. So how about I go through this one? I'll put up multiple or polynomial regression one more time. I'll go through a small example, and then we can start there. Okay, great. So we talked about so polynomial, so regression. Okay, and so the input here is going to be x, y, where in this setting we'll just say x is a set of real numbers, and y is also a set of real numbers. Well, just for now, I won't complicate things too much. This could be an n by d matrix. Well, actually, I can talk about that later today, or we'll see it later in the semester. We'll do a version of polynomial regression and classification later, and we'll I can also mention then how to generalize this. And then so then the output is going to be this model M alpha, okay, and this and so this will be of the form where I'm going to take in one of these elements of x, and this is going to have to look like alpha 0 plus alpha 1 times xi1 plus alpha 2 plus xi squared plus alpha p xi to the power p. Okay, so the difference in the polynomial regression is instead of fitting just a line, which is linear in terms of the x value, so it's an offset of some linear term, I'm allowed to have polynomial terms. So times the coefficient times the xi squared and so forth times alpha p to xi to the pth power. So I can go up to the pth power for some choice of p. Okay? And so this seems like it's much more complicated than just the linear regression, but I can think of writing xi into some sort of vector of 1 xi squared up to xi to the pth power. So now I have a p plus 1 dimensional vector. Okay, what should I call this? I call this xi of p. Okay, so this turns into a p plus 1 dimensional vector, and now this model M alpha of xi is just going to be a dot product between some alpha vector times this xi p vector, and now this alpha vector equals alpha 0, alpha 1 up to alpha p, right? Which are, so this alpha here, which describes this model, is all of these coefficients, which is the model. This has to apply for all data points. And this here is described by this vector. Okay, and then the goal, like before, is we wanted to find the choice of alpha which minimized the sum of the squared residuals. Okay, so, but you know, just to drive this home, I thought I would write up a small example. Okay, so let's say that y is going to be, the input here is going to be 7, 2, 3, and 5, right? This is x1, x2, x3, x4, and then the y values might be 2, 7, 6, 3. Right, so this is equal to y1, y2, y3, y4. Okay, and let's do the expansion of this into xp. Right, so now I'm going to write this as x tilde p of y, and then I can run the multiple linear regression on this. So this turns into, first, this matrix here. The first column is going to be all ones, like we did before. The next column is going to be x1, x2, x3, x4 coming down here. I just copy those over. Okay, and then the third column, if I said p, we'll do p equals to 3. So we'll go up to third power, right? So this will be 49, 4, 9, 25. And then the third power, gave myself a hard one here. What is it? 3, 43, 8, 27, 1, 25. Okay, so this is xp, sigma, and then y is the same as before, right? So y is unchanged. Right, so once I expand this out, now I pretend that this is just my input data, and then I can solve for alpha as xp tilde transpose, xp all inverse, xp tilde transpose, and y. So I just apply this linear algebraic closed form solution, basically this kind of general concrete way of just expanding this simple data.
Does it, I think you might have missed the tilde on the xp.
Oh, here, yes, yes.
Just want to double check.
All of them, yeah. Yeah. Okay, good. And again, just review while we have this all up here. The goal is the alpha in RP that is the, I'll call this alpha p star, which is equal to the arg min. It's the alpha in RP. Okay, so the p plus one-dimensional vector, which is going to minimize the sum goes I up to n of of this model minus the yi value squared. And so we would call this term here the absolute value of this term. So if I put the absolute value around here, then this term is the ith residual. In this case. Okay, and I can write this because this is a matrix form. This is equal to arg min alpha p plus 1 of this is actually dot product, so it's x p alpha minus y squared. I can write it this way as well. Because this is a dot product of each of the alpha, the model is basically applying this dot product here, and this is the expansion that you see in each of these rows. Then the ith term from this is a vector, an n-dimensional vector here, is aligned with the ith term in y, right, which is this guy. So I can write it, and then the sum of the squared things is just the 2 norm squared. Okay, good. Okay, so I can. Okay, unless there are specific questions about this, I can go through homework questions and then, or other questions, and if we have time, I can derive this formula, which involves a little bit of calculus, but might be informal. All right, so let's start with homework 2. All right, so the first question on homework 2 was, put it over here. You have a random variable x, and the two things you know are the expected value of x is going to be equal to 7, and I know that the variance of x is equal to 2, and I wanted to get an upper bound on the probability that x is less than 5. Okay, so I want to get an upper bound on this probability. Okay, and so the tricky thing about this, so I said we need to apply one of the 3 bounds that we had. And the tricky aspect about this maybe was that before we always said that probability that x was greater than some quantity. Right now we're saying it's less than some quantity. And so you have to figure out which bounds apply. So the right answer is that you can apply so the Chebyshev inequality. That just requires the expected value and the variance. And then in order to get less than 5, you can go and say, well, this is less than that x minus expected value is less than minus 7, right? So this is inequality. I've subtracted 7 from both sides, right? And so this is less than or equal to the probability that x minus expected value, the absolute value is less than 2. Okay, so this says that this is the probability that it's less than minus 2. But now I'm saying the probability it's less than minus 2, or it's less than. So it's now
Greater than 2.
greater than 2.
Add this to that.
Yeah, so because I flipped the sign here, right? Let me add in another step. Let me get my eraser. Let's say this is equal to the probability that x minus expected value is less than minus 2. Okay, which is equal to the probability that expected value x minus x is greater than 2. Okay, when I multiply by minus 1, that means I flip this sign as well. And this is less than that the absolute value, expected value of x minus x is greater than 2. Okay? And now this is the form of the left-hand side of Chebyshev equation, and I know inequality, that this is now less than the, what is it, the variance of x divided by this term squared, 2 squared, which is equal to 2 over 4. Okay, so doing this was a little bit trickier, but this involves some algebra. And, okay? And then why can I not use the Markov inequality? Well, the typical form of the Markov inequality I use, it requires that if you want to bound x is greater than something, x has to be positive. But you could put a different lower bound on here instead. You could say that x is greater than some value b. But if I want to say it's less than something, I need x to have an upper bound instead of a lower bound. Okay. So that was also a little bit tricky. And for the Chernoff-Hopting bound, I need to know that x is actually strictly bounded between 2 values. And I don't have either of those.
I had two questions. And then my first question is, for this example, if we didn't switch the expected value in the random variable, we'd get the same answer, 1/2, is that right? If we weren't to switch the inequality, we would have gotten the same answer.
Yeah, so as long as you get to here, right, and inside the absolute value, the order doesn't matter.
Yeah.
Right, so as long as you drive, and these are equivalent inequalities, or at least this one's, this inequality is more restrictive than this one, so as long as you get to this one, then you're fine.
Okay.
So there's different ways to get to that expression, but yeah. So as long as you get to here, then this is the input to the left-hand side of Chebyshev, and you can apply, and then you can apply this.
Okay. My second question was for the inequality of the probability in the x is less than 5. If we had, would the probability of x is less than or equal to 5 and the probability of x less than 5 be the same thing, since the probability where something equals a number would become infinitely small?
We don't necessarily know that the variable is continuous. The variable might be discrete. Okay, all we have is a variance bound on here. So it's an upper bound, and the upper bound is we get the same upper bound, but it doesn't mean the probability is actually the same. So I don't want to say the probability is the same as if so. These are not necessarily equal.
Okay.
Okay, if it's a continuous random variable, they're don't want to say equal because there's some weird technicalities and these sort of things, but they're effectively equal. But I haven't said whether x is discrete or not. I can apply this bound even if it's not discrete, even if it's discrete, but I'll get the same bound.
Okay.
So I'll get the same answer. So I can't technically say this, but I can use either of these will give me the same bound.
Because this gives we're never given the information if it's discrete or not. And then even if it was continuous, you said that there's still some technicalities where it might not be true.
Well, so I wrote this because we don't know if it's discrete or not. I would probably accept you saying they're equal if it was continuous. I would. The technicalities really don't matter in this course. They might technically be equal. I'd have to. I don't know. I'd have to. There's some stuff with measure theory I don't remember some cases of when some bad situations come up. But the issue is I don't know if they're discrete or not. So I don't know if these are equal or not. But I can effectively apply the same bound. The bound applies for the general continuous case, and it's only an upper bound of what's going on.
That makes sense.
Yeah. So I'm going to apply this inequality does not care if this is a less than or equal than, or it's just a less than. Okay. Or it's, in particular, this greater than or greater than equal than, it doesn't care.
Okay.
Right. So to apply this, it's going to give you the same kind of
This may be a foolish question, but is the answer, would you expect the whole class line, like the probability of the absolute value of e of x minus x is equal to the of x 2, or do you just want 1/2 of the answer? Like what would be expected for the answer? Just 1/2?
I would like you to say this quantity is less than or equal to 1/2.
Okay.
Right, so I don't just want 1/2. I'd like it stated clearly what you mean. And I hope you should drive your work.
Right.
If you just wrote down the answer magically, I'd probably accept it. But I'd just because unless I explicitly say in the question to show your work, but I recommend you always show your work because otherwise, even if you make a simple mistake, you'll lose all the points. But then if you show your work, you should do a complete derivation where you start with this on the left-hand side, have a bunch of inequalities, and then get to this on the right-hand side. Okay. Right, so that's the right way to show them.
So we have an absolute value of the Chebyshev inequality, which can be rewritten into two inequalities, which to show there. But in the homework at the end result, I derived my answer 1/2 from one of the two inequalities that was rewritten that does not have an absolute value. And I still got to the correct answer, but is that not correct? Because I was deducted some points there.
Yeah, so I mean, there do exist one-sided bounds for Chebyshev, which are effectively a factor 2 better here. We did not talk about them. If you got to, that should probably give you 1/4 if you used that bound. If you used a bound, if you went straight from here and applied a one-sided Chebyshev inequality, which you could do, I believe, then I think the bound should be 1/4. It should be 1/2. But you have to be careful using those, and so we didn't introduce them in the class.
I was just going to say, I also use that method, and I also end up with 2/4 and 1/2. Because I solved for epsilon, assuming that epsilon plus 7 would end up getting me 5, so that I could solve for epsilon and put it back. And then I ended up with a 2 or 4. But
right, so
it's appeared somewhere.
If you use the bound from the book, which is what I expect you to do, you should have used this bound ahead of absolute value. If you use the bound from outside the book, which is okay, you should have cited that, and I would have expected a different result.
I started from there,
which would have been okay.
Is how I
Yeah. Yeah. What?
I said it's pretty easy to prove the one-sided if you just have Markov and Chebyshev.
Yeah. So if you use that and derived it, it's fine. For the purpose of this class is to kind of introduce you to these sort of inequalities, and I wanted to keep them on this simpler side. I think the first time you see them, they're kind of complicated enough already. Yeah, so I'm not saying it's necessarily hard, but I just there's a lot more beyond there. So there are dozens of varieties of these that I'm not going to go into. Okay, so this I think will not be on the quiz, because it's not the sort of stuff covered in what this quiz will cover. Do you have any questions about stuff directly applied to the quiz? The linear algebra or the linear regression stuff?
Just in general, we get those questions that are like, here's matrix A, add a column that'll make it all, inversible.
Okay.
What's the right? I mean, I know you can want to do a Gaussian elimination on it and figure out what it would be, but what's the most time efficient way to encounter on the quiz?
Yeah. So that's a.
This takes a long time with Gaussian.
Yeah, I don't expect you to do Gaussian elimination on the quiz. I might give you columns which are. So I mean, in principle, I could say, here is A, where and I'd say fill in the x's so that this becomes an orthogonal matrix, right? And this you should be able to do, right? This would be something, these two columns being orthogonal means that if I took a dot product between them, it's going to be 0. It's going to happen 1 times 0, 0, 0 times 0, 0, 0, 1 is 0. And so I need that to hold for this column as well, and it needs to be a unit vector if it's going to be an orthogonal matrix. And so the answer, say x1, x2, x3, is that x1 equals 0, x2 equals 1, x3 equals 0. So this would be a reasonable thing for me to ask. So you'd have to know that this has to be unit vector, it has to be orthogonal to those, and this is something you can calculate quickly. But I mean, in general, you should do something like Gaussian elimination, or you can do like, there are other ways to compute this, I guess. There's the Gram-Schmidt process is the way of orthogonalizing vectors, and that's probably technically the right way of doing this, some version of Gram-Schmidt, if you've seen that in another class, but we didn't cover that in this class. Right, but in case you had a question, that two things, and orthogonal, so matrix has to be squared, has to be all columns have to be so unit vectors, and has to be all columns have to be orthogonal. Have to be orthogonal to each other. And two vectors P and Q in RD are going to be orthogonal if and only if the dot product PQ is exactly equal to 0.
Is that orthogonal or is that orthonormal?
Orthogonal is this requirement. Orthonormal just requires that the columns are unit vectors and they're orthogonal, but it does not have to be square. So you could have fewer columns than rows.
I thought the orthonormal factor was just that it had a unit vector, like they were orthogonal matrix that had a
okay, so an orthonormal matrix A n times D. Okay, an orthonormal matrix must have D less than or equal to n, and the columns need to have two properties. They need to be unit vectors, and they need to be orthogonal. An orthogonal matrix has orthogonal rows as well, which you get out of this. But this one does not have to be a full matrix. It might have a subset of rows. For instance, a column unit vector is an orthonormal matrix. We will see orthonormal matrices when we talk about SVD and PCA. We will generate these for low-rank approximations. So that's why they're important and they come. But otherwise, orthogonal matrices have a much richer story. They show up a lot of other places.
How did you get the x2 again?
X2, yeah. So okay, so in order for this to be orthogonal, I know it has to have these three properties. It has to be square. It's already square. It has these. That means the same number of rows and columns, right? The columns need to be unit vectors. Okay, so the first two columns are unit vectors because their L2 norm is 1. This third column needs to have an L2 norm of 1. Okay? And the third restraint is they have to be orthogonal with each other. So it has to be orthogonal with this column. And if that is true, it can have anything in these two values as long as this guy is 0. And because these two are 0, the dot product with this subpart is going to be 0. So this term itself has to be 0. So this one has to be 0. The same argument, x1 has to be 0 because of the first column. And then the x2 can be anything at once, but I need it to be a unit vector. Right? So that in order to be a unit vector, 1 is my only choice. So technically, that's how you derive it. You can see why if I have things other than 0s and 1s in here, this is going to be a little bit more complicated to then do the same sort of derivation because it becomes a set of linear equations you have to satisfy. Maybe even a quadratic equation because of the L2 norm. And so that becomes kind of messier to work out. I won't ask you to do that on the quiz. So that could be a fun homework question. But the right answer is Graham-Schmidt, which we don't cover in here. So.
As a comment, for the orthogonal matrix, you can see column or row. You can use row as well.
Oh, I could drive it with the rows.
Yes.
Oh, so then this has to be a unit vector. This has to be unit vector, which means this is going to have to be 0. This has to be unit vector. So that has to be 1. Yeah, that's another way to derive it. Yeah. Okay, yeah. So if I just had one missing row, I could just force each row to be a unit vector, and that should solve it as well. Right. So that would actually be an easier way in this case. Yeah, if I thought about that, it would be feasible to ask this on a quiz, but again, probably trickier to come up with that. So I probably would ask that on a quiz. Oh, back there first.
So I have a question about the multiple variable linear regression. So similar to the polynomial simplicity here, would it be like the dual problem where you have like, if you take like the first column for that matrix is all ones, and then for the other columns too, they can be like different values. They don't have to be like powers, like exponents like we used earlier.
Right. So in the polynomial case, I fill out these columns by creating these exponents. Right. In the multiple linear regression, I'm basically given these values, and the 1 is implicit. That's not something I've given. I have that in front. That way, this term in front, which is not multiplied by anything, the offset term, well, now it's multiplied by 1. Multiplied by 1 doesn't do anything, but it means that the model is a dot product, right? And then it's easier to work with, and that my closed form solution, which I erased, is I could drive that without worrying about thinking about the offset. So that's why we do that.
Would it, so we were saying that in the orthogonal matrix, we were saying that the vectors have to be orthogonal, and then we're saying that their dot product equals 0. Isn't that the same thing as saying that the vectors are all linear independent?
Well, them all being orthogonal is the same as them being linearly independent. But linear independence does not enforce that they're unit vectors.
Oh, okay.
Right? So I could have put 0, 2, 0, and that would have been linearly independent, but this would now have been a unit vector.
That makes sense.
Yeah.
Did we go over determinants?
I put them in the book because I need them for definition for the later in the book, but I don't think we need to go through them. Yeah, in order to define the normalizing coefficient for a Gaussian distribution, you need a determinant, and that's an important enough thing that I thought I would define it. But it's something that measures something about the scale of the matrix, kind of like a norm. But I don't think it's a norm. I'm pretty sure it doesn't count as technically a norm, but it's a different way of measuring essentially the scale of the matrix. All right, how about I pick one more question from the book, unless someone wants to pick one out. Because I don't think we're going to go through the
These are multiple variable regression problems.
Sure, yeah. So do you have, is there one in the book that's I could do on the board, or?
I don't know.
So I think I just have a. Okay, there's question 5.2 is a multivariable regression problem without actually, it kind of touches on important parts of the definition. Like, I'm not going to ask you to kind of, to actually solve for alpha on the quiz, right? But so this one might be a good thing. So this is Q 5.2, okay? And it says, so I've got x and y, and x equals 3 column vectors, x1, x2, x3, right? These are, so this is in n times 3. Okay, and okay, so I want to run linear regression simultaneously using the 3 variables. Okay. So, no, this actually involves using a data set. So that's probably, all right, so if I have this, let me just elaborate on this a little bit. Each data point will looks like x1, xi, yi, where xi equals xi1, xi2, xi3, and an example of that might be 3, 2, and 7. Okay? And the important thing is a model here, m alpha of xi, is going to look like this dot product here, where if I expand this out, this is 1, xi1, xi2, xi3 dot product with alpha, and this is 1, 3, 2, 7 dot product with alpha, right? And this alpha here might be 6, 3, 2, 4, right? This is also going to be a 4-dimensional vector. Okay, so then to compute the model, I'm going to ask you to, I could ask you to compute this dot product. Okay. The other aspect here is that some data point yi might be equal to 8, and then the residual of Ri is going to be m alpha of xi, which is this term minus yi, and so that's going to be this dot product 1, 3, 2, 7 dot alpha minus 8. Okay, so refresher, this is what multiple linear regression is doing with some data. And I'm trying to minimize the sum of the squared of these residuals. Yeah.
For the dot product, shouldn't those be swapped around? Like, shouldn't the alpha be on the left side and
the dot product PQ is equal to dot product of QP.
Oh, okay, sorry. Okay.
Right, so I can write this in either way, and it gives me the same answer, right? Because I'm adding stuff up, and each term is a element-wise multiplication. Multiplication is commutative, which makes this commutative as well.
That makes sense.
Right, this is equal to 1 to d of pi qi, right? And it is equal to okay. Yeah.
And so I'm just making sure on the residual, after you compute the dot product of 1, 3, 7 with alpha, you would just subtract 8 from that answer, right?
Yeah, you'd subtract 8, and now that'd be the residual. Yeah, and I would only ask you to do this calculation if it was pretty simple, straightforward.
How did you get the alpha?
The alpha, this is for a fixed given alpha, which is determined by the model.
Oh, okay.
I won't ask you to solve for alpha. There's an equation you should all be able to look up and do, or do in Python. But I might give this to you as a 4-dimensional vector here.
So all we need to
It
do
would be given if I wanted you to compute something.
so all we want to do is just to apply that alpha to whatever the x that thing curve.
Yeah.
Okay.
Okay. So I'm going to erase this. So because there might end up being a pretty similar question on the quiz. Okay.